Now, I want you guys to basically just memorize this. Memorize and recite this, essentially. A catalyst lowers the increases the rate of reaction by offering molecules with an alternate reaction pathway with lower activation energy. So just remember this. What it's saying is that what the catalyst does is it lowers the EA. How does it lower the EA? Well, the molecules don't have to react by colliding together anymore. The catalyst allows them to react in another mechanism. For example, maybe the catalyst attaches to both of these things, and brings them closer together. So this would be a new mechanism with a lower activation energy. Cool. So instead of going down a long straight road, the catalyst basically says, I will go down this short and windy road instead, over here. So a different pathway, but I end up at my same place. Actually, a better analogy would be like this. So an arc, or like that. Okay, and I want you guys to draw this graph over here. So again, it's a reaction coordinate, right? So you have progress of reaction and energy over here. So essentially, I'm forming the same reactants and products, but my EA is now just lower. All done? Cool. So one thing to note is that, one, the catalyst is not a reagent. So it's not a reactant, it's not a product, it does not get consumed or produced in the reaction. So that's the definition of a catalyst, essentially. So it shouldn't get consumed. Two, a catalyst does not change the distribution of molecules themselves. So with and without a catalyst, the distribution should look the exact same. You can imagine what a catalyst does by looking at, essentially over here, this Boltzmann distribution. So what a catalyst does is, imagine here, this is before, and this is after. So the shape of the distribution isn't changing, but I'm just pushing the activation energy barrier back. So I'm moving it back over here, and now you can imagine this greater proportion of molecules will have sufficient energy compared to before, which is just this much. Right, a lot more molecules will have sufficient energy to react. And finally, I just want to talk a little bit about catalyst and activation energy. So sometimes you'll see that it actually goes via a kind of a squiggly pathway. So maybe what it does is, instead of going from A to B, right, it might form A, so it goes to AM, goes to A star, and then goes to B. Right. So it doesn't matter that it goes via a longer step. What matters is that this activation energy over here is smaller than this activation energy over here. So remember what I said before about activation energy. A higher activation energy means a slower reaction, and a lower activation energy means a faster reaction. Cool. So an example of how a catalyst works is over here. This is the hydrogenation of ethylene or ethene. So we have C double bond to C, so C2H4 and H2 over here. So what happens is, one, hydrogen adsorbs onto the catalyst surface. So basically it forms kind of like a weak bond to the surface of the catalyst. So the catalyst could be some metal like platinum, palladium, something like that. So first, H2 gets absorbed and the H to H bond breaks and forms H bond to the metal instead. Next, the ethylene bond is also adsorbed onto the surface. So the C to C double bond over here actually forms this bond over here instead. So it becomes C bonded to the metal and C bonded to the metal. And then what happens is that since they're so close together, now they can react. Now the hydrogen can bond to the carbon, and this hydrogen can bond to this carbon, and form and give our final product, ethane. Okay, so here are the steps. One, hydrogen and ethene molecules adsorb onto the surface. Then the bonds between the hydrogen and the ethane are weakened due to the interaction with the surface. So because these bonds are weakened, they're easier to break. Right? So this encourages the formation of new bonds, and also they bring hydrogen and ethane close together in proximity. So sometimes biological catalysts, so like enzymes, right, they'll actually bring two separate things close together and allow them to react that way. So catalyze the reaction by that way. So hopefully what you can see here is, instead of this random C double bond to C H collision occurring, right, they need the collision to occur like this. They're now having these two bond onto the metal surface, where they're close together and physically more likely to react. So this is an alternate pathway of reaction.